Okay, Assalamu alaikum, shabab. Welcome back to the class. Today we are going to start chapter number 4. As you see in the screen, this chapter is entitled Deflection and Stiffness. Deflection and stiffness, shabab, is a very important topic, a step in the design process. And what does that mean? It means that, literally, ya akhwan, it means that you might design something which is safe from, let's say, static failure. And like the theory, von Mises, and so on. But from a deflection point of view, it may not be. Now, what does that mean? It means that the stresses generated in the body because of the loading are not critical to cause yielding, but the body is deforming, okay, in an, let's say, not good way. One good example of this, you can have a beam, a shaft, which is very long, and you couple it with one part, let's say it's a motor, and the other part, or the turbine, and another part is a generator. And because the shaft is too long, it will deform. Now that deformation, it will have a little curvature. Now that little curvature may not be a big problem in terms of stresses, but it can cause too much problems in terms of vibration. So deflection should not be looked at as stresses. It's different. Okay, that's something I want you to understand. So let's see how far we can go with this. So what are we going to do? We're going to talk in general about spring rate, deflection and tension, compression and torsion. And then we'll focus on deflection due to bending. After that, we will talk about strain energy. And then we will talk about very important theory, which is the Castigliano theory. The name is Italian. There is a G. I think that G is silent. I don't know. If it is not, then I am just saying it Castigliano instead of Castigliano because it's much easier for me. And then we will talk about, if you recall from C203, the statistically indeterminate problems. We will basically use this Castigliano theory to determine the deflection in beams and, component. And then we will use this theory also to determine the reaction in statistically indeterminate problem. Because if you recall, the whole story behind the indeterminate problem is that you have like 4 unknowns and you only have 2 equations. So you need to generate another 2 equations independently in order to use, you have 4 unknown, 4 equations, and you solve them together. That was done by deflection analysis, basically. Then the last 3 lectures, the last 3 topics will be dedicated for compression member. What are compression member? We spoke about them previously. Basically, columns that are subjected to compressive loading, causing them to fail. So this is one whole topic, okay? Now, with respect to the spring rate, it is more or less an analogy which is trying to explain that material actually behave like springs, especially when we talk about elastic region. and the relation between the deflection, how much extension is going to is going to result from the application of the load, might have a linear relation or nonlinear relation. And this is some example showing you here that, for example, in A, for for a beam which is, you know, simply supported and being subjected to a transfer load of F, okay, the amount of deflection, okay, is linear with respect to the force. But there are cases, okay, if you put rollers, there are cases where the deflection become nonlinear, as you see. This is the deflection Y. And this is just showing you that the relation is not linear always, okay? That's one thing. Now, the deflection, which we called Y, you know, not in this example, we called it Y, which is the amount of displacement happening to the body. We are going to call it delta. That delta, that deflection, is a big word. It is not extension. Do you understand? It's not something getting longer only. No. Rather, the word deflection means if you take something and you twist it, the amount of deformation happening due to the twisting is also deflection. If you pull something, it gets longer. That amount of elongation is deflection. If you compress it, it gets shorter. The amount of shortening is also called deflection. So it's a very general word. And without getting into the derivation, if you remember, the deflection, the famous deflection equation for a member being subjected to a force tension, okay, is related to how long is this member and how much is the force, which is FL, divided by the cross-section A. What is the cross-section? And E. E is the modulus of elasticity, which is very interesting. This tells you that deflection is not like stresses. It's when we talked about stresses, we never talked about material. Stresses are a relation between geometry, the shape, the force, and that's it. They get generated in the elastic regime, okay? Now, you know, the geometry, the area, whatever. When we calculate stress, we say F over A. What is the material? Is it plastic? Is it not? We don't care. Now, in there, we are talking about a stress, okay? Now, that stress, of course, I mean, it's very simple. When I say F over A, I am talking about an elastic regime. Now, we all know that the stress, when you apply higher load, it is not going to be, this is the prediction of F over A. As you move on, you put more load, you go up, you more load, and you go up, and you go up. But in reality, we know that stress is going to, after yielding, is going to follow a different path. Okay? So the deflection is a function of the material property, E. And again, we're talking about elastic. Do you understand? That's why we have E. E is an elastic property. Now, so based on this equation delta, if you look, L, A, and E, if we take them aside, then we can actually call this one like a spring. And if we call this one like a spring, the K, which is the inverse of this relation, it's A over E, AE divided by I, then we can use the analogy F equals to delta K. That's basically what we are trying to do, just like the spring. Okay. Now, also the deflection, okay, for the torsion is T, which is the torque multiplied by the length, but this time we divide by the modulus, which is rigidity or shear modulus G, and instead of using area for loading, which is tension, we use J for torsion. You can predict that if the deflection for moment is to be deduced, then it should have M, the moment, it should have I, the moment of inertia. That's how I want you to think about it. So we will talk about this later. What is important is that if you recall, the deflection, which is basically how things is deforming, is related to it can be related to a distributed load. You have a distributed load, you get different deflection. So a beam sitting on whatever support, if you apply distributed load on it, it will deflect differently than if you apply whatever, a concentrated force. So that's the idea behind the deflection. And how does this deformation shape, this shape, become recognized is the following. If you recall, I know you may not like this, but the relation between a distributed load, which is a Q, over EI, E is the modulus of elasticity, and I is the moment of inertia, is related to the fourth derivative of the deflection in Y with respect to X. And shear force is related to the fourth derivative, moment is related to the second, and then the deflection, that which is here, if we talk about beam and bending, the beam, when you bend it, the deflection is actually rotation. Why? Because the beam is straight, and when you bend it, it curves like this. So the reality is that you just change the angle of the beam, its angle with respect to the horizontal. I know what you are thinking. You are thinking about the deflection, which is delta, which is how much down did it go. That deflection is also going to be measured. We'll see. So basically, you can either, that's the beautiful thing about this equation. If you relate the deflection with respect to the moment, you will measure the slope. If you relate it to a single force, you will measure how much down this will go or up, as we are gonna clearly see. And this is just to show you how the relation is being derived over here. So this is a linear shear force becoming a second, degree deformation in the moment diagram, and then we will have the slope going to a higher order and a higher order as we move on. Now, this is, of course, the relation between Q and the deflection. Do you understand? The distributed load. This one is this is basically the differences. That's why we have a fourth order, a third order, a second order, and then a kind of zero order. Okay, this is just a review. Now, if you remember, I am not going to spend time on this. This is for in the slide for you to refresh your memory. If somebody told you that a simply supported beam is being subjected to a moment which is a function of a distributed load W, and this is the moment distribution. Basically, the moment distribution is like a moment diagram, okay? From x, which is less than or equals to L, the length of the beam, and it's greater than or equals to 0 for the entire beam, a simply supported beam. Then what do we do? If you recall, if we want to, it says here, determine the equations for the slope and the deflection of the beam. The slope at the end, the maximum deflection in the middle. So what are we going to do? We go back to the equation that we explained previously here, although I made this so messy. But we say, okay, if we have a moment equation, okay, then basically M is equal to EI multiplied by D2Y divided by D square, dx square. So that's basically what are we going to do? We're going to use this equation. And if we write down the moment, and then basically what do we need to do? And we need, in order to find y, because nobody is interested in d2y over dx squared. So if you want to solve this differential equation, what you need to do is to integrate. So since we have a power of 2, a derivative of second time, second order, then we need to integrate, if you recall, twice. And when we integrate, we use indefinite integral. There is no x, y to z, whatever. So, and because of that, the first integration will introduce first constant. The second integration will use a second constant. And then what do? We substitute the boundary condition by knowing, for example, for a simply supported beam like this, okay, for example, that the deflection here is equals to 0. We substitute the deflection equals to 0 at that length, and then we find the first constant. And then maybe we take the deflection, knowing that this is a simple supported beam, that the deflection in the middle will be maximum. And so the derivative there will be 0. And that's how we find the second constant. If you remember, so this is basically what did we do? We integrated it twice, the equation of the moment. And then what happened? Of course, as you see over here now, what did we do over there? We said that basically d2y over, sorry, let me clean this up. So this is what did we do? We just said that we multiply this by this. So what do we have? We have EI multiplied by what? dy, okay, 2, which is equal to m dx squared. So then what happened is that if we integrate this and integrate this, then I should have wrote the integral because m is a function of x outside over here. So what happened over here? We will have EI dy. That's what we are going to get. And then we will have this as m, which is WL over 2x minus W over 2x squared, then dx. So we integrate this, and that's how we get the constant. And then we integrate again, we get the other constant. Now remember over here, this one, when we integrated it twice, since it is EI dy squared, when we integrate it the first time, we get EI dy. When we integrate it again, we get EI y. And that's the y, which is what is the, how far down along the y direction the beam will go. Okay? Now, Then what do? We apply the boundary conditions, and when we apply the boundary condition, we can determine C1, which is the constant, integration constant number 1, and the constant for integration number 2. Then if we do that, we can find an expression for y. Now look how powerful is this equation. This tells you that at any location from 0 to L, you can just tell me where do you want to know. If the beam is deforming like this, this equation is telling me that I can find how much is y here, 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 infinitely, many points. Anywhere you point, I will tell you how much is y. You understand that? Now, you may think, why? Why are we doing this? Why? In the end of the day, it's integration. And look, ya shabab, we are mechanical engineers. One of the dearest machines to us is the turbine, right? turbine يا شباب بكل فخر يعني الميكانيكال انجينيرز لما سووا التوربين I think they can claim يعني انه maybe it is one of the top 3-5 machine in the world يعني there isn't anything like a turbine ممكن space shuttle yeah but turbine is definitely among the first few top machines ever made by human يا شباب التوربين operate for several years non-stop sometimes. Its inside temperatures is 1,600 to 1,200 something degrees Celsius. The material there is under huge pressure. And do you know, I'm going to tell you an information. A turbine has a little blades, right, that rotate. It is estimated that the amount of stress on that blade while rotating at that huge temperature for many years, non-stop, that's why we have electricity, okay? It is estimated roughly that each blade is hanging an elephant, nearly an elephant, one big elephant, and it's working. We fly from here to Australia, 18, I don't know, 20 hours, 40 hours, I don't know how long. Amazing. Okay. So that turbine is made with high precision. When I say high precision, if you go to Aramco and see them while they are repairing their turbines, they speak about the clearance between the blade and the casing. صح التوربين عليه casing. You don't see the blades. They are inside. The clearance between the casing and the blade measured in thous. هم يقولوا يسموه thous. Thou is 1/1000 inch. And that turbine has a shaft which no people can carry. And it deforms because of its weight. It can have a diameter of 30-40 centimeters, something like that, if not more. So it deflects elastically. It deflects. And when it deflects, خلاص خلصنا يا شباب. If it deflects, it means it went a little bit down. And if it went a little bit down, I am talking about several thous maybe, it will start rubbing on the surface. وخلاص خرب. راحت الملايين كلها. راح, it's gone. This is very important matter. Very important matter. Even if the gap is too high and there is no friction, طبعا الفريكشن حيخرب البليد, حيولع فيها يعني. لأنه هذول الماشين يا شباب they operate at 30,000, 20,000 RPM, 20,000 revolution per minute. Go and see the RPM gauge in your car. It's 6,000, 7,000. This goes 20, 30,000. And it has very expensive coating, very expensive material, and, you know, shutting down the electricity on people. We have hospitals, and can you believe it? another thing is, even if it is safe, because the deflection is spacing is okay, it will rotate, it will vibrate, and then it will cause another problem. So the idea is that this equation for the amount of deflection is very important. And then ya shabab, if we take the derivative of this one with respect to x, the solution itself, if we take its derivative with respect to x, we are actually getting the slope. Now, why slope is important? We'll talk about it, inshallah, in chapter 7, but you will have both the slope and the deflection. So you can find from, خلاص يا شباب, احنا we're engineers, huh? You convert anything to me into equation. I use my mathematical magic in order to get you number. What is the maximum? What is the minimum? Is that right? So we can find the maximum, the minimum, and that's how we obtain those little tiny equations. The maximum is as simple as 5 multiplied by W, L to the power 4 divided by 384 EI. Amazing. Very little tiny equation. You can bring your calculator. Actually, you can use your phone to calculate how much is this deflection. You don't need to integrate in the field. في المصنع يا شباب. You don't need to. We work so hard to make relations very easy for engineers and practitioners. المشكلة عندنا وين؟ إنه إحنا يجي واحد من الطلاب يقول أنا ما سألت حقين أرامكو ما يستخدمونه هذا. Don't get it wrong يا شباب. Aramco buys the turbine. They don't manufacture it. And if Saudis يا شباب يبقون طول عمرهم يشترون, يعني this might change. One day inshallah we might have our own factory here which will fabricate them. And if it fabricate them, يعني ذا ME-307 بيكون the most important course for the kingdom. With exaggeration طبعا. There are other important courses. But when you design it, you are the one who's going to use the equation to make the calculation. فأنت اللي بتيجي بتاخذ المعادلات وتعطيها أرامكو انجينيرز تقول لهم شوفوا لو صارت عندكم مشكلة أنا أدري إنكم ناس ملولين وما تحبون الانتجريشن خلوا علينا. هذا المعادلة الصغيرة حطوا فيها الأرقام وتطلع معكم. That's what you're going to do. You don't blame them. They are engineers just like you. But they are working in the field under the sun وبرشر وكذا. They are not sitting in an office trying to design. ما هو فاضي لك يقعد يسوي integration. But don't get it wrong يا شباب. It's because we buy everything we don't care. But the truth is we should not treat ourselves this way. And this to answer a question of students who say, why are we doing this? Why? إذا تبقى تشتري طول عمرك, for another 1,000 years, you always buy, depends on other countries. That's what's going to happen. So never think like that. Now, there are other ways to deal with deflection. There are in many situations, even practical situations, there are, since, by the way, I told you this in chapter number 5, that we are mostly operating in elastic regime. So don't think that what I'm going to talk about is different. The principle of superposition can be used, especially by engineers in the field, in the practice, to solve sometimes very difficult problems. Okay? But you need to be careful that this principle is only valid for elastic regime, which is very fun. We assume that the machines operating in our industry are under elastic regime. So this superposition does not give you an imaginary solution. It's a very practical one. So what superposition is telling us? It tells us that you can just split problems into little tiny one. Okay? يعني ببساطة superposition, the best example for it is this. إنه يجي واحد وانت تروح الكافي شوب وتقول نرجع لسالفة الكابتشينو. And you tell him, I want a cappuccino. يقول لك في حلين. الحل الأول اني انا احط الشجر والمويه والحليب والكافي يعني. وخلنا نفترض ان احنا في القرن التاسع عشر ولا ما ادري، ما عندهم ماشين، ف making a cappuccino will take a half a day، يعني بدون مبالغه خلينا نقول نص ساعه. and تقول لا والله انا بركب الخيل حقتي وبمشي ما ابغاكم، صح ولا يا؟ So we're talking about the age when there are no cars. So the other way, say, tell you I have another solution for you. And you say what? شو خذ الشجر وابلعه، خذ الكافي وابلعه، وخذ الحليب واشربه، وخذ الماء الحار واشربه، وبس خلصنا يعني. You took all the ingredients. It's not gonna taste like coffee, but at least your tummy there down, just the whole thing mixed up, right? It's almost the same thing with superposition. So in superposition, if you look at the example in the slide, what it tells you that if you have a problem like this, where you have a concentrated force and a distributed force, okay, you can actually, if the loads are as such that this problem is entirely in the elastic regime, you can actually solve the problem as if there is only a distributed load, and solve the problem as if there is a concentrated load. Then if the problem, طبعا احنا نستخدم superposition for deflection. Then if you want to know how much is this little tiny deflection, you measure the deflection from here, and then measure the deflection from there, and then the total deflection will be delta 1 plus delta 2. It makes sense, right? If it is elastic. Now, but you may ask a question. You say, how is it easier right now? I have one problem, now I have two. Well, the good thing about superposition is that there are a lot of standard solution for it. So for example, if you look at the slide, this is the solution, which is, by the way, in your textbook, at the end of the textbook. على فكرة يا شباب, let me stop here. الchairman كلمنا، أنا طبعا حاولت أتواصل مع البوك ستور، والظاهر تجيهم مئات الاتصالات يوميا ما يردون. And we talked to the chairman, and the chairman said that the university, the registrar or the bookstore, either did it or will do it soon, and they will send another email to all students who did not respond to the textbook issue. Okay? So student can indicate that they need to receive the textbook. Now, I know some of you told me that they did not receive the old textbook. That issue, I still don't know about it. Yes, يا سلطان.
احنا جانا ايميل ثاني بخصوص الكتب.
طيب.
معلومات، اعطيناهم معلومات اللي ما استلم يعني.
Okay, great. Yeah, that's good. So it means they did it. So this is for the student who think until now that they did not receive email. طبعا student will, some of you might claim that they didn't receive email. And I don't know. You don't read your email is having a problem or something like that. So, okay. Now, so what are these? These are the solutions provided in the textbook for linear deformation, elastic deformation, for many simple cases, around 20 to 30. If you go to handbook, you may see even hundreds of them. So if you have a beam with a length L, cantilevered, do you remember the word cantilever? What does it mean? It means that this beam cannot be displaced along the y direction or the x direction, and it cannot even rotate. So it is fixed end condition. And on the other end, we have a force F. The force F is acting at the end. So what is the solution? The deflection equation is y, And the moment the maximum deflection is given to you as a final closed form solution, and even the moment equation, the shear force diagram, the bending moment diagram is also given to you. If you look at the other one, this is a cantilever beam with an intermediate force. That intermediate force is it is at a distance A from the cantilevered end, a distance B from the free end, and again, you have the deflection equation and you have the maximum deflection equation as well. The shear force diagram, the bending diagram, the moment equations, and as you expect, it can go on and on and on. If I am not wrong, I think I provided all of the the deflection solutions. I think there are 20 in the book in the back of the slide. If I'm not just gonna shuffle through them. So when you have this, that's it. You're done. What you need to do now, for this example, you need to find a solution, a ready solution for a distributed load, a ready solution for a concentrated force shifted. It's not acting in the middle. Solve both of them, add them together, وخلصنا. Do you see that? So let's go to an example. This is an example for what seems to be a complex matter. We have a beam which is subjected to a distributed load P0. Yes, يا فيصل.
دكتور عندي سؤال بس قبل لا تبدأ بالإكزامبل. Can you go back to the previous slide?
This one? Okay, this one?
Another one.
Okay.
So, as the force become closer to the cantilever, the deflection will be smaller than when the distance is larger, right?
صحيح, yes.
At the end, يعني.
Yes.
Okay.
And the good thing is that the equations are exactly gonna make this happen for you, because they have been derived based on the integration process, everything. So somebody has done a lot of work for too many problems to give you the final answer. Okay, Faisal?
Okay, thank you.
Yeah, welcome. So this problem, as you see, we have a distributed load, P0. We have a concentrated moment in the end, and we have a concentrated load at the middle. The moment is given to us in terms of P0L square. The concentrated load is also given to us as P0L. So this is just to make the problem a little bit easier, okay? It's a function of, everything is a function of P0, but they have different constants. The length of the beam is L/2, and what do we want? We want to know the deflection here, okay? So let me simply, ya shabab, tell you how are we gonna solve this. You will see the solution later. So basically, you will have a cantilevered beam, okay, with this is how are we going to split the problem, with a single moment. That's one deflection. And then a cantilevered beam with a distributed load. Now, if you go back to the problem, the distributed load is going upward, not downward. Okay, this is very weird, right? So you have this as a distributed load. And then the third problem is the beam with a concentrated load. Do you understand? So basically, what are we going to do? We are going to find the deflection for this one. If we go back to the solution, we will find that the deflection for this one is actually P0L square divided by 2EI. How did we get this? Well, let me show you. There is something very important you need to notice. أخطر شيء يخطأ يعني الطلاب يقعون فيه في مشكلة، وأنا ما أتكلم عنكم اليوم كطلاب. I want to talk to you as engineers in the future. You go يا شباب تفضحونا وتسوي غلطة كذا. You need to be careful. This equation is made for what's supposed to be a length L, and this is X, and the moment value is M, and it is acting up like counterclockwise. So it wasn't difficult. If you look at the equation, Y maximum, which is at this point, is M at point B multiplied by L squared divided by EI. Now, L is the same, the length of the beam اللي عندنا في السؤال, L over 2 plus L over 2. So I will substitute L with what? With capital L, زي اللي في المسألة, okay? And E is the same, E. I is the same, I. MB بتكون ايش؟ بتكون المومنت equation. What was the moment? M0 كان قيمتها P0 L square. Do you understand that? So if you go now to this, what will happen is the following. You will have to have L to the power 4. Do you get my point? Why? Because we have L from the equation, and we have L square from the equation, and we have L square coming from the moment. Now this is also messed up. Always, students make a mistake. Superposition is supposed to be easy like this. Most students make mistakes in superposition, unfortunately. هذا السهل الممتنع. Now, if you go to the distributed load, we have a solution for it. It's acting downward. The solution for the distributed load, what give W, which is the distributed load, multiplied by L to the power 4 divided by 8 EI. Now, if you go here, the distributed load value is P0. So it's not very challenging. The deflection for this is going to be what? P0 multiplied by L to the power 4 divided by 8A EI. However, it is positive. Why? In the equation there, it is negative because it's acting downward. This one is acting upward. So be careful. Those equations, you need to match them with what you have. So you will have another distributed load. The other deflection is for a free beam acting in the middle. If you go back to the solution, match it with what you have, you will end up with -5 P0 L to the power 4 divided by 48 EI. And then what should you do? In order to find Y at point C, you just sum them up. P0 L to the power 4 divided by 2EI. طبعا يا شباب احنا الآن لازم ننتبه. هذا positive. ليه؟ لأنه البيم بيصير له deflection كذا. هذا positive because the beam will deflect كذا. This is negative. Do you see that? Some of them will push up, some of them will push down. The end result, whatever it is, يعني اللي أقوى هو اللي حينتصر. So this one plus P0 L to the power 4 divided by 8 EI, and then -5 P0 L to the power 4 divided by 48 EI. Understood, يا أخوان? Okay. Now, there is another example. This example is a little bit more challenging because what are we going to do? Because of this support and the distributed load is acting on the left and then the concentrated force, if somebody look at this problem, you would say, can I deal with this problem like this? And then this is one beam, and then another beam which is simply supported. Can I deal with it like this? Yes, but this one, the diagram that I plotted over here is not correct. ليه؟ لأنه إحنا يا شباب when we cut a beam, what do we do? What do we do when we cut a beam?
Shear and moment.
We substitute. Exactly. And when we substitute a shear and moment, we're basically, يا أخوان, putting it as a fixed condition. ليه؟ لأنه الbeam is fixed from this side and fixed from that side. Do you understand? So this problem is going to be like this. Do you see this? Now, so let me show you how are we going to deal with this condition. But I think we're running out of time. Let me ask you now to switch on your webcams, ya akhwan. Gonna turn off mine, and we're gonna take the attendance. In the remaining whatever few minutes, we can talk about this. Okay, did you turn it on, ya shabab? Switch it on, thank you. Faisal?
Yes, present.
Okay, Yusuf?
موجود.
Yusuf?
Present.
Yeah, I can see you. Thank you. Ahmed?
موجود.
طيب حمد؟
حمد موجود دكتور.
No, حمد sorry. Yeah. علي القحطاني؟ علي؟ يوسف؟
Yes.
I think I saw you, يوسف. Yeah. ماجد العباد؟
Yes.
Yeah. حسين العلي؟ Okay. محمد؟
Yes.
حسن؟
Yes.
عايش؟
Yes.
مبارك؟ دوسري؟ مبارك؟ أحمد؟ غزالي؟
Here.
حجي؟ الحاجي سوري علي الحاج علي It's not here. معجب
Yes,
yeah, I
دكتور.
can see you. سلطان الحربي
موجود يا دكتور.
سلطان
موجود يا دكتور.
اوكي سلطان لا عبد الله الحجاب
موجود.
سلطان
Yes.
هوشان
Yes.
yeah I can see you. فارس
Yes.
عبد الرحمن
Yes.
خالد العتيبي
موجود دكتور.
عبد الله العوفي
Yes.
فارس قحطاني
Yes دكتور.
ثابت قحطاني
Yes, دكتور.
علي رمضان
Yes, دكتور.
هاشم سادة
Yes.
ماجد
دكتور.
محمد
Yes, دكتور.
and أحمد سلطان
Yes, doctor.
مشعل يامي مشعل وليد وليد you are here right
Yes.
and محمد
Yes دكتور موجود.
عبد الله
Yes دكتور.
and أحمد سنبل
Yes دكتور.
yeah okay I think it's time يا شباب so thank you so much we'll see you in next class إن شاء الله.
Doctor, I have a small question, please.
Yes.
When we you substituted m by b0l to the l squared.
Okay.
Is it final formula from the integration?
ايش تقصد يا فيصل؟ لحظة, let me share my screen again. Okay. You mean this, right? This.
Go.
صح?
The first example we solved.
Yes, this one. So which problem do you have? I mean, we split it into 3 problems, right?
Yes, this one.
Uh-huh.
He said m0 is equal to b0 all squared. Is this given for this specific problem or it's general?
Yeah. لا. It was بدال ما يعطيك قيمة أعطاك إياها as a function of L squared.
Oh, because I thought that the load is related to the moment.
لا. It's a constant. يعني it's a value, it's a variable which is related to the distributed load. هو
قطع صوتك يا دكتور. يا شباب اللي معي تسمعون الدكتور ولا لا؟
لا اختفى صوته.
أهلا يا فارس, معليش seems
ما في
like
مشكلة.
my iPad got disconnected from the network. Did you understand me, Faris?
Yes, it's just given for this problem, a constant.
Okay, yeah.
Thank you very much.
Yeah.